Yeah, good to see Navjit Singh. Yep. Don't see you often on these calls, I guess. And good to see our next gen Vivek Garimalla as well. So,
Navjeet, take a seat here. खड़े क्यों हो?
you're muted, Navjit. Yeah. Yeah, when you stand up, the ceiling looks real short, you know. Okay, why don't we get started? I'm sure more folks will be joining in. It's 5 past the time we were scheduled to start. So I guess Sundar needs no introduction. I think you all know he's a world expert on engineering design and advanced manufacturing. And I mean, as just a short context, I guess we might have forgotten a lot of our, and Navjit, if you can mute, there seems to be some background noise from your end. So, I mean, we might have forgotten a lot of our undergrad IITK courses, like maybe fluid mechanics or heat transfer, except folks really in the field. But we never forget our TA 101 to 104, 101 with our T-squares, like orthogonal drawings, and TA 102, it's kind of eye-opening concept of engineering design, and 203 and 204 are manufacturing processes, where 203 manufacturing by material removal, and 204 by manufacturing by material addition. And in fact, most of Sundar's talk will be on, I think, additive manufacturing. And I mean, in the 50 years, we learned TA 101 through 104. I mean, we have progress from CAD design to maybe AI assisted design and additive manufacturing and all that. So over to you, Sundar.
Thank you for the introduction. And I also want to thank Kusha for hosting this Zoom meeting. I put together a set of slides I typically use when I talk to audience or kind of familiar, but not all that familiar. So mine, I'm trying to take away from too much research topic, but they will be kind of, you'll see some of our work that our lab has done. But primarily my objective is to see if we can reach some kind of appreciation for the advancement in manufacturing and primarily in additive manufacturing. So let me just start by defining a few things. I hope
Sundar,
everybody can hear me. Yep.
Sundar, before you get started, what's your preference for questions?
Oh, anytime. Anytime
Okay.
people can either, Arul can, he's a host, so they can put in the chat and maybe Arul can check it and then share it with me. Or if it's more appropriate, Arul can decide whether that can be held back to the end. It's a free conversation, so I have no, anybody can ask at any time they feel.
Thank you.
Yeah, I suggest, I mean, you all can interrupt anytime. I mean, if it's too many interruptions, I'll interrupt and moderate it. And I'll keep an eye on the chat, and as appropriate, I'll read out those questions or ask you folks who wrote the question in chat to read it out. Go ahead. Over to you, Sundar.
All right, I assume that everybody can see my slides, so if not, let me know. That the talk is kind of put together with an overview for the different terms that people use, Industry 4.0, 3D printing, additive manufacturing, and then take a kind of a look at what's so special about additive manufacturing, or the different types of additive manufacturing. And that will kind of take me to designing with additive manufacturing. That's an area where our group has been doing some active research. And what's our kind of the kind of a aspirational goal? It's the digital twin for manufacturing. But I will also close with some of the work that we did on the educational side, which is kind of what we see as the challenges in dealing with additive manufacturing. Let me start by defining Industry 4.0. Probably some of you will be familiar with it, but it's nice to kind of look at it in a cartoon way and kind of illustrates the advancements we have made. So we can go back in time and we can look at a definition of industry, probably somewhere in 1780s, the first revolution that's being associated with mechanization. A lot of the work that came from that was primarily the source of power was either steam or water, and that makes sense. And then 100 years later, we got into electricity, then it became mass production, and electricity was a driver behind a lot of things that happened. Again, it took another 100 years, then we started going into the third revolution. The date is a little bit fuzzy, but most people agree upon 1969. Electronic came into being, and IT and other things. So the automation became the real thing then. And within 50 years, we have progressed to Industry 4.0, which is being kind of in vogue for the last 10 years or so, which is primarily connecting the dots between all the things in IoT, robotics, industrialization, mass production, customization. And so that's where we are now. And a lot of people refer to the advanced manufacturing as the Industry 4.0. So you'll hear the term often in both academic and industry perspective. So I typically use sites for all the things I'm going to be talking about today, but this one you can find in the public domain. And this one I got from a colleague, and I don't have his notes with me right now. So this is a kind of take a deeper dive into the Industry 4.0. There are all kinds of things here. Primarily, it's the ERP, the Enterprise Resource Planning. That means you want to create an ecosystem where manufacturing is not siloed. With all due respect to Arul and all our remembrance of fond memories of TA, by definition, by referring to as a TA, it was decoupled from our education side. It was not physics, not chemistry. It was not mechanical engineering course or civil engineering course. Rather, it was clubbed as a technical arts. I still argue with people why that should be not the case. But be as it may, now if you see these things, lots of advancement happening in different things. I'm going to just zoom in on two topics for today, even though our group has worked in some of the other things. But my primary interest all through my career has been in simulation, focusing on design and additive manufacturing. We got into it about 10 years ago, when things were the right place, the right time, so to speak. So I'll walk through some definitions of additive manufacturing, come back to simulation as the driver behind the digital twin. All right, so what's additive manufacturing? It's straightforward. Everything is only because of Arul mentioned CAD. It's a driver for additive manufacturing. You can go back in time. And I know there's been jokes going around in different groups about orthographic views and all those things that we did as part of our engineering drawing. That is so passe. Everything is digital 3D, and CAD came into full existence in the 80s. That got me into my interest in design. And now that's a driver behind everything in additive manufacturing. So this is the formal definition. But oftentimes when you look at it and you will see this, it makes perfect sense because everything, even I would mention, or everything we learned about is subtractive manufacturing. We took the block of materials. We did drilling, grinding, lathe work, any machining. Whole definition of machine shop is hit the block and reduce it to a part we want, successful, and happens. And we refer to that. We can think about it and look back and say, hey, that's all subtracted from the block of material. Whereas additive manufacturing is either layer by layer, mostly, and you take the material either in powder form or liquid form and construct it layer by layer. And that makes sense because now you are able to do layer by layer, construct the object. And if you're successful, the waste can be minimal. This is just cartoon way of showing the same. Another way of looking down and looking at this problem is the subtractive process material removal is top down. We take from the top layer and go down to the bottom layer. Whereas if we go with the additive manufacturing, it's bottom up. So you start with the base layer and go layer by layer to the top of your part. So you can look at it both ways, top down and bottom up. But if you go back and talk to people, especially in a non-engineering circle, you hear the term 3D printing. That makes sense because everything can relate back to the inkjet printer or anything like that and say, okay, instead of depositing ink, now we are depositing material. So in some sense, it is 3D printing, but it's a synonym in some sense it makes sense, but in the engineering sense, especially where I look at things, it doesn't communicate what capabilities for additive manufacturing, which is we can produce professional functional parts. I'll explain that in a couple of minutes. And it clearly distinguishes from all other processes we are more familiar with, referred to as subtractive. So that additive manufacturing is a term that is used in kind of professional circles, and people will use it to replace parts from a functional perspective. Okay, so if you actually search for the terms 3D printing and additive manufacturing, not so surprisingly, you'll get different types of results. So if you look at the left in the 3D printing, it's almost all our CAD representation. There are more physical objects that you can see, feel, touch, and I would refer to them as toys or illustrated examples. Whereas if you see the ones on the right side, the additive manufacturing, you can see that it has some metal and other things kind of showing up. And these are more functional parts. Even the skull that's shown there, it's put under some kind of stress. So you can see that, hey, this is meant for replacing how we can do certain things certain time. Okay, so you see somebody has a question.
No, I just put a comment.
Okay, great. All right, I'll let you be the judge of that.
Yeah. Yeah, I'll monitor
there
the
is a
chats.
fundamental difference between 3D printing and additive manufacturing from how we plan to use it. So everything that we can see in terms of gadgets I refer to are 3D printing, and everything that's a functional replacement for a part that we want to use in our industry setting or other places would be the additive manufacturing part. Okay, so then why? I will talk a little bit more about our NAE study, which is interesting in its own merits. But here are some slides that I'm going to show from a friend that I work with, and we put these together. So we compartmentalize the rationale for additive manufacturing into 4 buckets. First and foremost, I keep talking about it, is we can produce functional prototypes. So not necessarily in the production phase. The prototyping phase, it can be cost prohibitive to invest in casting or do anything more large scale, whereas functional prototype using 3D printing or additive manufacturing can be an excellent start point. We can produce very complex parts. I'll show some examples. And truly, this is where I think the best use or the most optimal use of additive manufacturing is it puts innovation in front of all manufacturing engineers rather than at the back end after all the innovation is done, they just go make the part. So in that sense, it can push the boundaries. We can rethink about our materials. We can rethink about our CAD representations. We can rethink about part structures, everything. Of course, we can also, it's viable because low volume. It's whether you produce 1 part, 1,000 parts, the part is proportional, not otherwise, as in the case of traditional. Last but not least, this is some of the project we work with, actually Navy and also one Air Force, is that maintenance and repairs of parts that are sometimes not even in production anymore, or you're in a place where you can't afford to wait for the repair of parts to happen. So again, those situations, additive manufacturing is an excellent alternative for traditional way of manufacturing. Okay, let's just look at each of those a little bit more. This is kind of a cartoon way of showing. The one that you're seeing as a bottle opener, you can 3D print it. That can be nothing more than a paper mache and can not actually do the job for you of opening the bottle cap for you. Whereas I can produce it using 3D printers in most labs, and they will functionally replace any bottle opener we see in the market. So it's not just the visual prototype, just covering the aesthetics, but it's a functional prototype that helps demonstrate the core features. So that's the first and foremost example for why additive manufacturing. Again, we've done some work with medical device companies, and advancement is just absolutely mind-blowing. Most places where they can produce replacement parts, which are light and strong and inert material, and also customized to each individual patient. And we've seen this in use all the time. but it is really happening. And last but not least, they found that these complex bone-like structure can actually simulate bone growth. So here, where we have taken a kind of a divergence from our traditional way of looking at it, is we are not constrained by the materials anymore. We can mix and match and produce material that were previously unthinkable. And so I can show you some examples of this. This I got this from the 3D printer.
So Sundar, in that particular example, what material is it?
This is the most material here will be the, I will tell you in a minute.
Yeah.
It's the one that we use is, it's a kind of a composite material, mostly ceramics and other things included, and I will get back to you on that. I don't have the top. I did work with the UMass Medical School on one of these for their implant, and I had to go back. But mostly we did with the ceramics and some other material mixed with it. I will get back to you on that. Good question.
Okay, thank you.
This, I have some examples to show. This actually came from our colleagues, and one of them is Lockheed Martin. This is not from them. This is the Brigade, because this has a nice illustrative video to go with it. We use an example. So they actually built this whole part using their 3D print, and this is the kind of a brake caliper, the single part, and they claim it can do the braking for up to 260 miles per hour. And they have actually, again, I have the website that show how it saves them. I have no verification for it, but it is often used as an illustrated example. And this is one of the coolest examples I have seen for producing complex parts, which are, again, not large in number as a prototyping phase or other things. It can be very helpful. The third one, again, this is something that is illustrative in by itself. It's not a complex part, but you only need a few parts. This is typically for our industry partners, especially Raytheon. I'm sorry to say that. Raytheon has been funding our research for the last 25 years, and all their parts are low volume, and all of them, they don't want to be having an outsourced place because of propriety, because of things they do, and even to enter the building, you have to have a US citizenship, all kinds of protocols they have. So for them, it's important to produce low parts, and so they have their own virtual reality center, and they have a few machines and stuff. So we help them produce some of these parts. Not producing is the easy part, but how to design them so that they meet all the specs. And last but not least, this is the cartoon example that we have of a part where you're trying to find a replacement part for your car. And obviously we put a kind of an old model call there. So the company is not in production, or the part is no longer available. Again, you can 3D print the part and run it, and people have done it successfully. This is one of the projects we did as part of an SBAR phase 2 and phase 1 with a small company. And our part of our work was primarily to not just use the replacement part. We were working with them on their naval system, where if the ship is out there somewhere miles away, how do we spot it? How do we do the inspection? How do we get the information back in the loop so they can have a kind of a digital twin set up in a small scale so they can find a replacement in-house there in the ship? And they successfully did it for a couple of parts, but post-processing, another issue. So it's still, I would not say in practice, but it has been explored. So those are the 4 main reasons of why we would use AM part. And this one is the one I mentioned. This is actually from the Rocket Lab, and it is a 3D printed rocket motor. And again, lots of news have come out from what they have done. It's been referred to as one of the first of its kind where they actually printed the whole motor using the 3D printing.
Again, Sundar, just so that I stay on top of this, 3D manufacturing, or like you said, the toy kind of facilities now seem to be universally available in what companies call maker labs. They have lots of 3D printers, and researchers can go and make fun things. But to make stuff out of titanium, steel, ceramic, how available are these in even, let's say, your university? If the student population wants to make things for their own projects, are these becoming more and more available? Are the operational costs
Yeah, well,
fairly trivial?
it's surprising for you to ask the question. That's my second part of my talk, and maybe that is kind of a interesting. I didn't pay you to ask the question. So if you hold the question for a few minutes, that's the second part of my talk.
Absolutely. Thank you.
First part of my talk is all talk, and second part is where I feel there is a gap between. That's where the challenges in AM will play a significant role.
And I have a small request, just like the earlier question, when you point to parts, if you could just say, one word or two on what the material is, because I'd like to get a sense of what is doable and what doesn't seem to be doable.
Okay, I have a couple of slides that will walk you through that in a minute. These are more like talking about the white part. Then they have hopefully that'll be helpful. If not, I'll try to spend more time on that.
Thank you.
Well, I will share this slide with us. And so if you take a look at it, it is not just talk. So exactly the question was right. The big companies, the defense industries are able to do this.
Is it only me, or I don't get an audio for this video?
Oh, okay. All right, hold on then. I'll skip this. Okay. It's not that important for now. So let's skip this, and I'll post this online for people to see if the audio is not coming through. It's interesting how they talk about it. Again, obviously, these are all big companies, and point well taken. Let me close this by the slide that just came to me about 2 weeks ago, and we had a guest speaker on this. This is a successful rocket fuel pump that just was published 4 months ago, August 20. No, that's 2025. Sorry, that's not right. So this is, again, they just got it done, and my date is not right. This is 2025. So this is the 3D printed turbo pump, and it's talked about it can have a maximum RPM of 95,000, thrust potential, fuel delivery, horsepower, part count, and they claim that they did it required 45% fewer parts, and it completed 15 different tests under flight-like conditions. So all this shows that technology is there. Technology is ready, and technology is offering a lot of potential for advancements. So now, kind of reflecting on the question, what are the different types of
Sundar, if I can interrupt, Ravi Rao has a question. Ravi, do you want to read it out? You're muted, Ravi. But let me read it out. Ravi says, in subtractive manufacturing, usually there is a finishing step. Is there a similar step for additive manufacturing? Also,
absolutely.
Can a part be used post-AM?
Yeah, absolutely. There's a lot of post-processing you need to do to make the part ready to use. Post-processing is part and parcel of all 3D printed parts or additively manufactured parts. Probably sometimes a little more than subtractive manufacturing, but those are all things that you can do in a small shop in your, it doesn't require, I'll talk about it. First and foremost, some of the work that you do in metal 3D printing all come with some kind of a support structure that you have to kind of take it away. You have to do some polishing, grinding, finishing, surface finish, all those things. You have to do some heat treatment to make them meet your expectations. So yeah, all of them require some to large extent of post-processing.
Yeah, thanks, Sundar.
Okay, here are what referred to as the ASTM standards, and they have 7 different families of additive manufacturing. I am not an expert on all of them. I'll highlight the one that I feel are most popular and kind of appealing from a perspective of functional prototype. So we have this photopolymerization, powder bed fusion, binder jetting, material jetting. And if you go through it, again, I'll share the slide. A lot of them will talk about what kind of material is a good fit for it. So if you take the polymerization, it's mostly photopolymer resins. And if you go into the powder bed fusion, it's plastics, metals, ceramic, everything. And each of them have the set of materials that are best fit for that. And obviously things depend on it. If I talk to a company like Puma, a lot of them are working in the binder jetting. A lot of the thing is that, they are looking at how to 3D print their shoes. So it's mostly all kind of a polymeric and kind of a thing. So each one has a thing. My interest, and most people who are looking at functional prototype, functional replacement for manufacturing, the most popular one is the powder bed fusion. So if you are curious about one type of additive manufacturing and see how things play out, I would say, hey, you know what, take a look at the powder bed fusion. You will find different names for it. And 10 years ago, we used to use SLS, which is a selective laser sintering. That was the primary name. But these days, everybody uses powder bed fusion. And there's another set of things that are continuation. The sheet lamination, exactly like how we do lamination for our other things, mostly plastic and some metal foil maybe. Extrusion is popular. It's just exactly you have the wired metal going through layer by layer. This one, direct energy deposition, that's another popular method, again, mostly for metal, sometimes for ceramics. It is used as a kind of a places where the powder bed fusion is not used. I would say probably DED is the one most popular. Of course, last but not least, kind of reflecting on the question as well as other things, nothing I'm saying here is replacing manufacturing per se. All you can think about in the future I'm seeing is the hybrid. Take best use of both. In fact, we have done a lot of work in saying when should you go into additive manufacturing, how to actually bridge the gap between traditional and when should you switch from A to B and how to make best use of both. So nothing I'm talking today is saying anything about traditional manufacturing. It's like maybe we can look at it as how to take advantage of both. So let me just look at the two processes I mentioned. Again, this is the direct energy deposition. So you can see that basically it is being fed through the wire or sometimes actually in the liquid form too. And you have the gun, and as the thing is being fed, you start applying the energy and deposit it in layer by layer form. So you have substrate and you have the base, and all those things are formed layer by layer. And so the feedstock can be a wire, powder. Mostly I have seen as a wire or a powder. The second one, this is where I know a little bit more about because I have actually seen the process, I have seen the machines, and I have been fortunate to work with NIST, who have been partners with for 10 years, and they have some really state-of-the-art systems. Is that here, everything, each one is a layer by layer. The powder is the layer. And basically you have the substrate and the layer, and then you have the laser beam that is reflected through the mirror, and you just deposit it. And it's all fascinatingly done through the CAD system that you have. The CAD drives the thing and dictates, and everything depends on the laser position, laser beam, laser speed, and laser direction. And that dictates the quality of the part you're going to get. Surprisingly, the cartoon version or the illustrated version is much easier than in reality. So the designing for and designing with AM is still a big challenge. The reason for that is multifold. Start with, we don't have a material.
Sorry, Sundar.
Okay.
Can you go back? I didn't quite understand the drawing. So I see the downward arrow with how the part is being constructed bottom up. How is the powder deposited? Is it deposited as a sheet and then stuff is just removed and then the laser comes in sinters? Or how does the powder? I see. So there's a sheet of powder, spread powder.
Yep. Each layer, there is a process where the powder is rolled from the tank. The roller will come and roll the powder.
Got it. I get it. And then you just sinter the parts that you.
Yeah. And then you push away the unused powder, so to speak, and the next layer comes in. Yeah.
Yep. Got it. Thank you.
And that's why you need not just a substrate, you also need a substrate structure. And this goes back to the earlier question. So because if you're looking at this, think of this as a 3D printed part, so each can be a different shape. That means you have to have some kind of a support structure that holds the part together.
Yeah.
And it's a lot of complicated things with the overhanging and other things. And yeah.
Got it.
Good question. Yeah, thank you. So this is where I have taken a lot of interest, and our group has done a lot of work. The first and foremost is the material. Primarily, you can do anything with the powder. You can combine the powder. You can get, and powders are hard to define in terms of material properties. Going back to, again, our favorite subjects of metallurgy, is that everything we learned about material is from, hey, material handbook. It'll say steel means this is a property. You look at ASTM, it'll define what steel property is. So if I machine it, I know the property is more or less the same. I know what the yield strength will be, what the material property will be, what the price transfer, all those things are known. But when you're dealing with powder, it's a lot more, uncertain about what the final product is. The second one, the design itself is not that much more traditional. A lot of things that we used to do, we used to think in terms of, hey, not possible. Now everything is possible. So I can show structures, and you have seen the motor that was built. This is complicated. So it's not easy for us to design in a more traditional way. The third one, the system itself has not been what I would call as authenticated. It is not validated. It is one of the biggest challenges. There are plenty of AM manufacturers, and each of them claim they can produce quality parts, but there's no verification. There is no standard that we can apply to say, hey, if I use this system, will I get the part that meets my qualification? And the last but not least is the process data. The process, again, you can probably remember some other things we learned in casting, or people are familiar with injection molding. It goes through so many layers in terms of its phase transformation to everything. It is hard to compartmentalize and categorize and qualify all the things. I'm not sure why he's doing this. Sorry about it. So we're going to focus on the processing parameters for just sake of illustration. So just the processing parameters itself, you have the laser type, you have the laser power, a whole host of things. And if I look at the material properties, again, there's a bucket list of things that you can look at as what should we look for in terms of metrics, qualification for a part. So one other thing that is still an ongoing discussion is how do we get to know the properties of the material as the process is doing it, not post-processing. We can always do it afterwards. We do the post-processing, we can go and do the testing and the prototyping and say, okay, that's the problem. But we want to design with it. That means we need to know a priori. So that's the challenge. And so the work that we did was trying to understand predictive models. This probably other people will relate to. This is the same thing all of us looking at. 10 years ago, when we started this, we used to refer to this as qualification. These days, we refer to this as metrics. That's more of a nomenclature change. And the second part is, so what's happening, which is what we used to call as a process control. These days, we refer to that as analytics or data analytics. And the third part is the what will happen, which we used to, again, in our glory days, call optimization. We switched to predictive analytics. So the predictive analytics requires us to have some kind of a model or simulation that will be helpful for us to a priori know what can we expect from the process. So if you think in terms of starting with the design that we have from our CAD representation, we build it, we go through the process, we set up the process. Okay, this is the laser speed, this is the laser, direction, and there's intensity, all those things, and we have a strategy for it. And we start the process. The building is step by step. Then take it out and do the qualification test, and you have the final product. But now, if you want to do it in situ, how do we do it? So now we want to build a model that could be helpful at any stage, could be used to gain some insight, and also alter approaches so we can do the best design. That's a hypothesis. So what we did was, this is again very simplistic, our approach is that we constructed two different sets. One we refer to as the white box. In that sense, it's primarily all based on machine learning. The second one is the first one is the white box, which is all based on physics, FEA, CFD, or anything that we know about the physics of the problem. The second one is the black box, where it's all based on data. That's the one I refer to as the machine learning or statistical model. Of course, neither one is an easy challenge, but we have a lot more work done in the black box side of things. So we teamed up with researchers at NIST. So we did the FEA model for us, the CFD model. So they use different types of continuum-based heat transfer model, powder-based thermal fluid flow model. So they were able to give us some physics-based model representation for what they expect the outcome to be. And then we construct our black box model. So we worked for 3 years, 2 of our PhDs and 2 of our researchers. We looked at it and we did a lot of different things. I'm not bore you with the details, but idea is that how can we build a hybrid, which we refer to as a gray box, where we make the best of both. So we can use the FEA model or CFD models to help us train the data set and collect the data and use that in situ to update the model while we are actually doing it, the process itself. So the optimal hybrid model, we published some work, it became the basis for a lot of work. And both my former students are currently at NIST now. So they are continuing the work, and there's still a big interest in NIST in terms of how do we quantify, how do we have metrics, and what should be our standards in expecting the 3D printed parts.
Sorry, Sundar, again,
Okay.
a bit slower than the rest, I guess. So go back to the CFD model. I didn't quite understand what exactly is being modeled in these 3 pictures that are down there. Is it the complete structure, or what is the effective powder layer?
Great, that's my next slide. Yep. Okay, good. So we did not look at the complete structure. So I'll tell you what we looked at. This slide will help you. This all we looked at was, again, that's a very good question. Most people think during the time of additive manufacturing, the best that you can get information about for the metrics you're looking at is the melt pool, which is supposed to reflect the quality of the part. The melt pool is what forms when you go a layer by layer. And the melt pool information will give you about the state of quality of the part later. And a lot of work has been done to identify melt pool as a kind of a single parameter that we can use to some hypothesize about the quality of our part. And so all you're focusing here is on a melt pool formation.
What is the melt pool in the wire model that you had? You were melting something and it was creating a puddle.
Oh yeah, this is on the powder bed fusion. So this is the powder there. And when you heat the powder and you form the part, as you turn the direction and change the speed, there will be places where you can see in this setup here. This is the kind of thing where you will see the different places will have different formation of the part. And if you zoom in, the reds are the one where they're showing it's a high melt pool is forming, and they are not kind of forming the metal immediately, so they're leaving that as a metal pool.
So Sundar, is that the microstructure or is the temperature
this is the microstructure.
Okay,
this is the microstructure.
Okay, got it.
And this is the one the scan pattern shows that these are the 4 places where you can clearly see the scan pattern has resulted in high melt pool.
High being topologically high.
Sundar, can you learn anything from the powder metallurgical processes?
Oh, absolutely. This is that's the one that the NIST group is looking at. Is they want to go back and see how the metal formation can lead to better material that being fed into the system. All we are doing here is the process condition mapping. We are not doing anything. We only assume the powder that is being used is given to us. But the material guys, in fact, the work that most of the work people in NASA are looking at is how do you come up with new materials so that fits our pattern.
Sundar, there's a comment from Raman Bhatia. Raman, you wanted to read your question?
Yeah. So there's a lot of work in the area of CAD/CAM. These systems have evolved a lot over the years, but with this, it sounds like a step change in what goes into a typical CAD/CAM system. Have you seen any evolution in these CAD/CAM systems like AutoCAD, CATIA, and so on?
Great question. Absolutely. In fact, from AutoCAD to CATIA to PTC to SolidWorks, all of them are rapidly changing the way the CAD systems are formed. So you will be surprised that you will not get any CAD system without having some section on additive manufactured part. And right off the bat, that will take you out of the materials selection from the box of material properties. Rather, it'll ask you to go through some series of steps to prescribe what you can expect out of the material. Because if you have a powder form, then you don't have any material property to choose. And if you don't have material property to choose, then you can't have an FEA. You can't have any kind of a stress where you find the maximum stress or anything. So the CAD part of the geometry part may remain the same, but nothing about the CAD part is the same. So the whole hypothesis, the paradigm shift is coming, in my opinion. And a lot of the people that I talk to in the industry, they are both compelled to change and also reluctant to change.
So just a follow-up to that. So like say you've got a part and you know what the design objectives are, what the strength is and so on that you're trying to achieve. Like does it allow you to select the right material, the right combination of the different things you got to mix to achieve that?
My reading of everything I know, CAD systems do not help you with any design decision making. It can only execute for you at best what you want. So you may have to go into much more than just a CAD system. You may have to have some kind of a design tool for you to help you with the selection of things. All CAD can do for you is once you select it and prescribe, it can help you to capture the 3D image of your thing or all the things. It can tell you what process you might go into. If I can actually tell it, hey, look, I'm going to use powder bed fusion, AutoCAD and even SolidWorks and CATIA, all those things will tell you, okay, then these are the things you should look at. These are the ways you can do and what kind of printer you have. It might, all these printers have kind of tagged along with it, but it cannot tell you what material to choose. I don't think it will help you with anything about the same thing. It cannot tell you whether you should change your dimension if you find you're not meeting your strength.
Okay.
But it can tell you where the strength is weakest.
Right.
Yeah, I would think that you would need, just like, again, my knowledge is dated, multi-physics models, where you're basically trying to figure out what the heat transfer, even, in a brake, I can imagine. It's not the CAD tool that is telling you how well the brake is going to perform, how well it's going to dissipate the heat, but you need to introduce other physics to essentially capture from the geometry.
Right, because some of these CAD systems have the finite elements and the heat transfer analysis all built in. So,
Good, yeah, I think you answered your question. They have all the analysis built in. So if you tell them, my middle kind of shows, if you tell them what your system is, it can come back and tell you what the melt pool you can expect, or you can expect what stresses can you expect. All those things you can do, but you cannot tell you what to change. It cannot help you design. You can analyze, yes.
So Sundar, along those lines, follow up. What is the status of integrating AI into this and maybe making those material selection design decisions real time, So
I think we're going to have a talk 5 years from now for me to comment intelligently on that.
Yeah, okay, got it.
It is all a work in progress. All of them claim they have some AI built into it, but nothing in meaningful way that I can speak about. All of them are working on it, and they are spending a ton of things. Because one good thing about these things is because of the CAD and we've done some work too. You can go to the legacy information and learn a lot from the legacy information that they have. Raytheon we work with. Every part they made, we converted to digitize everything. So everything they've done, they know exactly, hey, this part failed under this condition, doing this after this many years. So they have all the legacy information. So that part is easy. whether they have done anything AI about it, because I don't think, this is again my humble opinion being in design, I don't think any of them have quite figured out how to do design. So for me to tell whether they have used AI to do CAD-based design is for me a stretch.
Okay, thank you.
There, just sorry for coming back to the original question I had. So this is a temperature reading of a
Yes.
part?
Yep.
Okay.
And
And
this is just, yeah.
And a corollary question is, are, a lot of techniques were developed in other layer by layer fabrication techniques, like the whole IC industry runs on fiducials, test structures to test every layer that is put down or, processed. Is there something like that, given that you're doing layer by layer processing again? Is there something that you do to make sure that the parts, every layer is registered correctly, every layer produces the material properties that you desired when you put the material down at the end of that layer processing, etc. I mean, there's a lot of stuff that goes into, IC manufacturing.
That is the holy grail, Sanjay. But what I am showing now is we haven't quite figured out on a single layer or a single material property. So it is going to take a while before they figure out what you're asking for, which is more of a system-wide or layer by layer, or even kind of something that speaks to the quality of the part while the part is being made. Because the whole thing is going to be made in a fraction of a second. So for us to even get any information while it's being done, it has been a huge challenge.
Yeah, I mean, so the stuff to be looked at, I would say there's learning in the IC industry. They had to figure it out. Now, the speeds may not be kind of what like you're talking about, but you could do it every 10th layer or so, or something that.
Oh yeah, that kind of a thing we do. That is part of the reason why this project was focusing on melt pool. The things that you're mentioning, there is a lot of effort into kind of figuring out where, I'll show next slide, where are the most vulnerable places that you should look at. I mean, again, people who are in the FEA or material, they will know, look, you don't look at the whole part. You just want to look at the part where it is likely to fail, and you want to make sure that part won't fail, then you assume the rest of the part will be fine. So if that is your failure of the condition, you look at it. But if the cost reduction, then you look at where can I reduce the part and make it just kind of not as heavy, so I can reduce the weight, I can reduce the cost. So lots of different competing factors come in, and people are looking at it. If you're looking that way, yes, but not while the thing is made. It is done either before the part is being sent or post-processing after the part is made.
So Sundar, in interest of time, you might want to move on to your next slide.
All right, great. We'll come back to it. Okay,
yeah,
good.
Yeah,
There are a lot of good questions. I'll show. I'm not a single person looking at it. This is another kind of a graphical view showing the same thing that we did. Again, you have a physics-based model. You have some dimension reduction. You have some surrogate model. And again, nothing fancy here, very similar to what we showed with us fancy names, but otherwise same. But I want to highlight this. Paul Witherell was my former student. He's now a fellow at NIST. And guess who is his collaborator? Mahadevan, our own colleague, classmate, is a collaborator, and it's kind of interesting that it's a small world. Unfortunately, I think Mahadevan cannot join us today, but again, this is the work that not just I'm doing, but lots of people are doing. And I was thrilled to find that two people connected to me are working on the same problem. Okay, now I just showed you one project that we did for one type of things we looked at. Last 10 years, our group has done a lot of different things. I could have given a lecture on ontology. I think I would have partnered with our friend Shirish on that. He's done a lot of work, and a lot of things you read here, which are not going to bore you, but it is just what I showed you is one fraction of a problem that we face in using.
Sundar, you mentioned the name Sresh Netke or Sresh?
Netke done a lot of work in ontology. Yeah, we talked about it offline. Yep, he's done a lot of work on ontology, and that is again basically standard. How to come up with a standard for manufacturing, especially for additive manufacturing. What we look at are the metrics. What should be the language we should be talking about, and how do we interpret the same information given between two people?
Yeah, yeah, that's great. I didn't know Netcase's
Oh, yeah.
versatile expertise from blockchain to ontology. Go ahead.
So blockchain is, I think, today's interest. This is about ontology. He and I talked about 10 years ago, or 5
Sure.
years ago, I
Okay.
should say.
Yeah, okay, got it.
So the center that we ran, again, that was solved for the manufacturing, but we did a lot of work in aerospace, automotive, and medical devices. We teamed up with some 20 industries over a period of time and 7 universities with members. So we did a lot of work. 3 years ago, we closed the shop because it's a 15-year project. We somehow continue for 20. There's still a lot of things are going on, but a lot of our partners are in different places now. But taking a look back, this is Sanjay's question. The holy grail is how to come up with a digital twin for additive manufacturing. This is where the simulation, additive manufacturing, IoT, the 3 things will come together and form the basis for any design decisions we make using physics-based simulation. AI, again, this is a real question. This is the physics-based simulation that we learned and we all used for long periods of time. Design decisions, which is some of the questions that I've asked, and how can you have some kind of a dashboard that synthesizes the information so we can run the system that is running here while sitting here. And this is, again, the holy grail, but lots of people are looking at it, including our group. The same thing when I talk to industry, they don't see it the same way. It's just a disconnect. That's kind of leading to my second part of the talk. Again, this is one of our partners, Kinnard, works at Lockheed Martin. And whenever we talk about digital twin, we think what we think, this is what we think should be the digital twin. This is what they want. They basically want some creation to somewhere, somebody using it. They don't care how you do it, but the whole thing, they just want to have connected. And so it's very interesting how they do the digital thread. Again, they have nothing about AI, nothing about anything else, because they are worried about it. They don't want to use AI, especially in defense industries. They just want everything to be proprietary in-house. Anyway, they use this, they won't tell you. So it's a very different way how they look at it. But nonetheless, it takes me to the challenges we face. I only post some introductory things, and what we have done is a little bit of here and there. But this is recognized. This is the National Science Foundation, Resilient Manufacturing, a group that I work with. One of our team is now applying for funding from them. And they identified all these things as a kind of ongoing problem in making advanced manufacturing and additive manufacturing a reality. And so I don't want to bore you with the details, but you can see everything we talked about, everything you can think of is still an issue. But the one that kind of appealed to me, again, being in the academic setting, is what's the lack of skilled workers? And again, maybe that is tagged to a question, earlier question asked about the scaling the business. And I could have spent some time on it. I'll probably try to see if I can relate to both. The scaling of the business is, hey, every example I showed is probably done by some, large manufacturer or defense industry. What about the SMEs? What about the small scale industries? How can we afford to even have an additive manufacturing unit, let alone metal 3D printing? Okay, so this is kind of focusing on the America's advanced manufacturing workforce, but I can kind of use this when I went to IAC Bangalore last year. This is my talk, and they were kind of equally sharing our concern that, hey, manufacturing is not seen as a part of innovation. It's a disconnected workforce education system. That's why I want to kind of go back to our statement. All due respect, our manufacturing, all we remember is what we broke in the lab. It is the TA, kind of considered as a decoupled from what we learned in our classroom. It was also done in the early years, first and second years, where we haven't quite gotten the full breadth of our knowledge about engineering. And so that way, I've taken a deeper dive into it. I've become an advocate for it. There are 550 universities in US alone offer BS degree in mechanical engineering. There are less than 30 universities that offer undergraduate degree in manufacturing. And if I look at the 30, only 2 of them have any research component we consider as R1 university. So there is a disconnect. And most of the students in manufacturing, either they'll go to what we refer to here as a community college or vocational schools. In India, it's the same. They get sent to vocational schools and they get training. All of us got exposure, but never got expertise in manufacturing. I talked to a lot of people, so this is kind of a work, again, organized by the National Manufacturing Materials Board and NAE. And I'll just highlight our buddy here. Arul was the study co-director for us. And you can see the list of people, kind of half from industry and half from academia. We spent about 2 years, and during COVID, we did a lot of work. I'll again summarize things that might resonate with us in sense of my passion for why manufacturing is underappreciated. I skip it for the lack of time. So the things that we focused on was increased collaboration between academia and industry. Again, this is something that resonates well for today's engineering, especially. All our 5 years, I don't think we heard a single mention of an industry, at least I don't remember, because I don't remember a lot of things. Industry was never mentioned until the time we started applying for jobs. That's the only time anybody will talk about somebody got a job at this place at that point. Even the interviews mostly focused on what we knew or what we know or what we should know, but rather about nothing about manufacturing, nothing about what the industry expects us to do. In the same time, the experiential learning was also missing. We had some labs that I fondly remember is great, especially for physics and some of the materials courses, but nothing later on in engineering that related to what we learned in our classroom to how they get manufactured. So the experiential learning involves being in the lab manufacturing, what we refer to the capstone design today, where we actually produce things. And so that's something, 2 things that I've been talking about. And I looked at the courses in today's curriculum at MEDHEC, at IIT Kanpur here. You can see on the left, all these courses are familiar to us. Things haven't changed, which is good news and not so good news. But the manufacturing science and technology, it is, I'm happy to see as a required course, but just a single course. And I talked to the faculty who's teaching it and looked at the materials they cover. And you can see the materials that cover is all about more traditional manufacturing. Good. Traditional manufacturing should be taught to them. But they have an advanced course in 461 they have, but that's more optional course. But there's nothing really about what they need about advanced manufacturing. This is the TA 202. Again, a lot of talk about it. So I took a closer look at what they do. This is today's TA 202. And I didn't see much change from what we did. And maybe there is some change, but it's not enough, in my opinion, because the manufacturing is through the roof. It does talk about microfabrication, layered manufacturing and metrology. That's great. But I don't think enough importance is given to how manufacturing can play a role in design, in CAD, in everything we do in any engineering topic should relate back to manufacturing. So that's the same here. So we talked about it. Again, I'm going to skip this, lack of time. So we looked at it, a lot of things, and this is the thing that I wish that I had the opportunity, and I wish, the students today's world would have it. Actually do produce the part or manufacture the part or work with the industry where they can learn how to manufacture the part when they are doing their capstone, whatever course they're doing, whatever design they're doing. It'll be so illuminating and illustrative to couple both engineering and manufacturing. This is part of the reason why we find the skilled labor is a bottleneck for people to start their innovation or their small manufacturing company where they can start doing things, is because they haven't had the breadth of knowledge that will take them into that next phase. Okay, again, for lack of time, I'm going to skip. And, you can read the wonderful report that Arul put together for us, and I can share the link with you. You can read a lot more about it. And for sake of time, I'm going to skip so I can open for questions. Just kind of closing 5 minutes, I want to walk you through who I am. Even though I talked about manufacturing.
Sundar, if I can interrupt, Navjit
Go
had a question, maybe that's appropriate at this time. So, Navjit, you want to read it?
Sure. So, Sundar, you talked about the state in the US and some examples in India. A lot of manufacturing seems to take place in China. And I was wondering, what is the state of manufacturing in China? And is there a lot of advancement in AM, additive manufacturing in China? And also, it seems a lot of the companies, even on the committee, are defense, sort of Lockheed and others. So is this a lot of the funding, a lot of this work funded by defense? So two questions really.
You're very smart. I kind of this whole committee was requested by DoD. I probably don't have a slide. So the whole NAE study was requested by the Department of Defense. And what they felt was the compelling need for the government readiness in advanced manufacturing. So that's why the people in this list you're seeing are primarily from defense and academia. That's the first part of the question. That's the last question, second part of the question. The first part of the question, the advancement in China, it is a little difficult for me to get a reading, except anecdotally speaking. The reason for that is Srinivas at Georgia Tech will know this too. Somehow the manufacturing field, advanced manufacturing field in US is a lot more faculty from China. And that means a lot of our, even our own graduate students and otherwise, have shown a little bit more readiness and interest in advanced manufacturing than I would say domestic students and other international students. Same time, the number of conferences, number of publications, other things, if I take a look at them, again, they'll show quite a bit of high number of publications, high quality publications from faculty in China and faculty originally from China. Other than that, I don't know how the companies operate there or what they do in terms of production. Because as far as I know, I talked to one of the people that I talked to, I was kind of fortunate is in Apple, and they have the factory there, and he goes and every month he's there. He comes back and tells me that all the things they do there are exactly prescribed by what they want them to do from here. So he has not seen anything innovation-wise, but again, that is again anecdotal. Did I answer your question, Rajiv?
Yes, thank you.
Okay. So if somebody knows, they can share. I don't know. I can get you anecdotal, but there is no study that I know that has shown. Even our study didn't reveal. Oh, on the contrary, our study did reveal Europe is far more advanced than we are. Not in terms of just doing manufacturing, but how they have integrated manufacturing in their academic setting. So I actually went to a couple of places, Manchester in England and another place in Germany, to study the apprenticeship program. So they actually bring students, like if you remember our vocational schools, they bring those vocational school students to take that 1 year of prep work, they call it academic apprenticeship. And afterwards, they'll get their 4-year degrees or MS degree or PhD degrees. And if you do a PhD degree in manufacturing, especially, you have to spend at least 1 year in an industry setting, or you have to have an industry person in your committee, and the project has to be relatable to them. So they have done excellent work, in my opinion, in advancing, both academic side and industry side. Okay, here's where I am. If you notice that everything is design, that's who I am. So I'll just from cartoon way, again, lack of time. This is something 101. So every question you ask me, I think about it. Everything asked about design, I have no idea, but I have this slide that I use to talk about, what design thinking is. And, it's like knowing the what and the how, and how much versus, and, what should we do now, and who wants what. So this kind of thing that I talk to our students, lack of time. I'm already behind. This is another slide, again, be helpful for people from the decision-making side. Everything I relate back to when I talk to the additive manufacturing, I can't tell you whether to manufacture traditional way or to manufacture it, but I asked them to go through this exercise. I have a couple of things, they work with me, and we walk them through and try to compartmentalize. So what kind of metrics they use, what kind of preference they have, and what is their logic they want to apply, and we help them with the decision as best as we can, refer to as a normative decision-making process. But with the caveat that we tell them that this basically means that you will make the best decision. That doesn't mean it'll be the best outcome.
Yeah, I just have a kind of a tidbit here. I mean, when I first joined the National Academies in 1999, I became a study director of study funded by NSF. It was actually called Theoretical Basis for Decision Making in Engineering Design. So it's just interesting that you talk about
You
decision
also mentioned
making.
Josh
And,
Hazelrigg, so we have that
yeah,
connection too.
yeah, yep. Okay, you go ahead. Sanjay, you have a question? You want to read it out or summarize it?
Sure. If I understood what pitch you're making, I was playing the devil's advocate and saying,
Can you speak a little louder, Sanjay? I can't hear you.
sure. Sorry, I'm in a noisy environment. I'll try to speak up. So, if I understood the pitch you were making correctly about lack of research and widespread research going on, etc. With my experience or cursory experience in the IC industry, if you see a lot of and there's fairly advanced manufacturing techniques that go into this with making finer and finer featured structures, but a lot of the primary research is conducted within the confines of advanced tool manufacturers. So the tool manufacturers are making, I'll call it the sledgehammers and the anvils of today, but I don't think they're counting on, and the people who operate these machines are, at best undergrad educated, maybe they're managers, etc., into advanced process development, may have higher research education than that. But the tools themselves and capabilities are fairly advanced. And so why do I need to do research in every small academic university to advance additive manufacturing? I give you that knowledge of advanced manufacturing and its capabilities and challenges, etc., should be taught, but I'm not sure research needs to be conducted in small universities. Why am I wrong?
I still had little difficulty hearing you, but if I heard it correctly, you are saying, hey, why should research be done? Why can't just be knowledge and background information is sufficient so you can have the research done in one place and the execution can take place at the manufacturing floor?
Yeah, or the tool manufacturers are advancing the state of the art, but giving the capabilities by purchasing. People can get the capabilities of a titanium sintering machine by buying a tool from titanium sintering Inc.
This may address it. I mean, you need more time for that, more philosophical. The reason for that is the moment we call them tool manufacturers and tool, floor people of the manufacturing, I think it takes them away from decision making, and it is made it more sequential. That means all the decisions are made and then sent to them, and they make the part. What we are advocating for is an ecosystem where manufacturing is taken into consideration at the design phase. So you can say, hey, you know what, this is going to be manufactured this way. That means I can make this part with this feature. I can have this part do this. So therefore, this is the best way to do it. So because I have the knowledge about how the tool will be used in this particular production. So the idea is to make an ecosystem where the designer is not just kind of handing it off in a siloed way, but rather be more inclusive in the of manufacturing constraints and degrees of freedom.
Sorry. I understand that maybe traditional mechanical engineering or manufacturing of metal parts this is not the handoff to machine floor, etc., is a model that needs refining. But I would say learn from the IC industry, right? So if you look at fabs, a lot of it is run by operators, but the back end of it is where the design, the variations, process, testing ideas, what are we going to do, etc., is put in. But there is a separation between, giving people basic sintering capabilities of every metal combination that you can think of, and saying, okay, maybe I can modify a certain materials, or as Raman was asking, can I do drop-down lists of material choice and seeing what materials can these tools handle, etc. But I think there's a lot that can be learned by huge industries that run on layer by layer processing, which I'm not sure is being captured in at least what I heard. Now, it's a short.
We'll continue the discussion offline,
Yeah.
but I think so that's again, like I said, philosophical question. I'm happy to discuss. I can go in depth about why the mechanical systems are very different from the IC industry, and we can talk about it.
Okay, thanks.
We did take a look at it, but we had a lot of reasons why we think this is very different from what's happening in the IC industry. But we'll talk about it. Yeah. Okay. Now my last slide is more of a cartoon way. Again, I understand. This is how I look at everything about design is where we start with something, this is starting with Raman's question, maybe I found out that I need more strength, so I'm going to add more material. And then somebody decides more material can mean more ropes, not more platforms. And somebody can say, hey, more rope means more length of the rope and not just necessarily 3 different ropes. And there's always a joke about manufacturing. We try to see a symmetry in everything we do. And then, it's actually get executed. This is the sequential way of doing things can go wrong. So when it comes to the tail end and the user side, there's the only way to make it work. Whereas if I had put this person initially who is more knowledgeable and part of the ecosystem and work as a team, one can hope for innovation to happen much better. But I found a better example than this. This came from our SDG group, and I will let this speak for itself.
Yeah, both are really good cartoons.
I use this now in my class to say, well, why bother with any design? Just have an app. I remember in the early 80s, I think Dayanand, I think, kept telling us that every time somebody has to open the door, you had to make sure it doesn't fall. You had to have a thing. So no worry, kinematics and mechanics will always be handled. Will be fundamental to everything we learn. And the next day, I came here, and the first thing I thought, the local grocery store was a sliding door where I didn't have to turn any knob. So who knows? Okay. So last but not least, I know we take this for granted. I just want to give a shout out to our dear friend Sap. Working with him the last month, I came to know how much work he does behind the back to make it happen. So I know he's not here or maybe here, but thank you, Sap. And you're doing a phenomenal work. Appreciate it very much. So that's it. I'm ready for questions.
Kushru as well, if I can give a shout out to Kushru, who sets up the Zoom talk and all that, and then shares the recording after that. Yeah. So any further thoughts or questions? Any closing remarks? I see Kotesh. Yeah, go ahead, Dilip.
So I have some basic fundamental questions related to the AM process. So first question, can we mix materials? So for example, can I take a metal matrix and layer on top of that like a ceramic matrix or something like that?
Answer is yes. And in fact, there are machines that you can buy where you can have multiple different beds and you can feed different ones in different. I have an example of that. Let me see if I can find it. Yes, the short answer to the question is absolute yes. And you just have a different, you can have the powder bed mixed ahead of time, or if it's a direct energy deposition, you can do it in different steps. On this one, I'll show you. This is not quite what you're looking for, but here's the one. If you look at the jetting process, we have a jet machine in our system, the material jetting. So you can have different, oops, sorry, I'm not sharing it. I just realized. So see the one on the material jetting and the binder jetting, the jetting ones that you can get those machines that you can mix match. So you can see that drops coming through. So you can have different buckets sending you different material and you can make them composite.
Thank you. My next question is, can you provide directionality to the material properties? through different types of layering process or through the different type of additive processes?
Lot of work has been done in that, and absolutely yes. Everything I mentioned here, this slide I borrowed from someone. I may not have given credit. This is for my class. A lot of work has been done to connect everything on the left to everything on the right. I hope that addresses your question. So they can choose the laser type, power, and type of power if they want particular viscosity. They have kind of a NIST has it's still a work in progress, but a lot of areas it is fairly mature that people can just take and run with it. And if you buy a AM machine, that'll also have its own specs on saying, hey, look, this is what you can expect. If you do this, if you have this setup, you can expect this property to come out of. Did I answer your question, Dilip?
Yes. I mean, just to know this the basic question, and I can reach out to you separately for.
Yeah,
and
the more
I guess-
specific things, yeah, this is all more of a basic level because
Correct.
there's so many additive manufacturing equipment people, it's hard to keep track of what they're doing. Yeah.
And my
So
last
similar,
question.
sorry,
Sorry.
Dilip,
Let me
go
my
ahead,
last
finish.
question.
Yeah.
Just my last question. What's the effect of impurities like gases or miscellaneous material that was not part of the original matrix that you want to use?
Oh boy, I may not be the expert in that, but what I have seen is that the post-processing can play a significant role in the final quality of your part. So the post-processing where you remove all those unnecessary, unwanted material, powder, unburned stuff, any number of things can happen that can significantly affect the quality. But with respect to what happened during the process, it depends on the machine itself. The ones that I have actually had the cameras installed and stuff, they're fairly high end. So the reliability is fairly good. But I heard from people that, it is a hard thing for them to be knowledgeable about how to design for it ahead of time. So I don't know if I answered the question. I don't have any data on that, but what I know, that is a big challenge.
So what I'm coming from is like laser cladding or HVOF spraying and things like that, because they introduce a lot of errors or problems in the materials as you're coating them or something. So it's, you had talked about laser using lasers, but I'm familiar with the laser cladding or spraying, and they introduce a lot of problems along.
Okay, got it. Oh, in my opinion, the advanced manufacturing, especially on the metal side, the engineering of those systems are fairly advanced, and I've seen them the laser, speed, positioning, intensity, all those are well precisioned, and the CAD talking to them is so amazingly good. That itself, I am less concerned about. That could be a possible thing in the mid-range system, but the high-range system, they are done phenomenally well, in my opinion.
Okay. Thank you.
Just a quick
Now-
addition to what I thought Dilip was asking, but he didn't, was introducing anisotropy in the layers. So, I just throw powders are classic powders, but have people thought about imposing fields as layer deposition is done to align properties as you go?
Can
I don't know
you
if you
repeat
heard
the
that.
question, Sanjay? I couldn't fully, Arul, can you, I can't hear you well.
Yes, Sanjay, if you can talk a little louder and repeat that question.
So, can you introduce, are the capabilities of fabrication tools now such that you can introduce material anisotropy on a layer by layer basis? Powders are inherently random, but if I can do any alignment by using fields of whatever is applicable to cause layered anisotropic materials, is that something that's on the horizon?
I only know of support materials that primarily the objective is to code the geometry. So if your question is related to geometry, yes, there are systems in place to make every 3D printer part, in my opinion, the geometry always comes to very close position that you can expect. So the geometry is not
No,
an
it's not
issue.
about the geometry. It's about the orientation of
The topology.
no, even let's say if I'm trying to make some super magnets, how do I get the alignment to be right in a layer by layer manufactured structure rather than the random orientations I may get if I just do powders and sintering?
My answer is still the same. I still look at that as the dimensioning and tolerance that we talk about in manufacturing. From the dimensioning tolerance point of view, I think the 3D printer part are comparable in terms of geometry, tolerance, orientation.
We'll talk offline. We'll talk
Okay.
offline. I don't think I'm getting across my question correctly. So we'll talk offline. I was talking about micro orientation of the particles.
Okay.
Yeah, not about
The macro
topology or macro dimensions.
Then in that case, I'm not the materialist and I don't know anything about the micro level information. But I can, if you relate the question to me, I have the colleague at NES, I can get you the answer back or find you the information you're looking for.
Sanjay is trying to make the whole wafer using your process, and he wants to dope it too, and so on.
Why not?
Yes, I got you.
Okay, I get the question, but again, yep, at the micro level, good question. I don't know.
Navjit has a comment which maybe is a nice summary and conclusion of your talk. Navjit, you want to repeat it or read it?
Sure. So it sounded like, Sundar, you were advocating for cross-functional design and manufacturing teams, and the whole concept of, DFX, designing for manufacturing, and kind of which it's a classic issue ever since manufacturing began. Designers have designed and manufacturers have manufactured, and we have crises. Interestingly, Sanjay, one of my major projects even at Bell Labs was about that kind of when the product is redesigned and
absolutely, and design for serviceability, design for uptime, design, because it's not just make a part, throw it over the fence, and let somebody figure out where it goes wrong. I mean, there's a lot that can be done if you're going to say I'm going to build stuff, bottom up. Right in the manufacturing process, you can put in a lot of smarts.
All of us know that life cycle design has always been one of those things that we all talked about, but the reason this is more appealing today is, again, it all goes back to the 3D printing. That catches everybody's attention. So once you get them to the room, if you go around, you will notice that every place has a fancy looking additive manufacturing right as you walk into the manufacturing floor. They all want to showcase that. Oh, we want to have a meeting. Oh, can we have it adjacent to that so I can show you how we are doing things? Then you ask them the third question, so who's using it? How many people are using it? Oh, yeah, that one person we hired to use this. All the other 1,000 manufacturing people, they're all in the other place doing their original thing. So yeah, absolutely right. This is hoping that with this advanced manufacturing, and about the Obama's investment 10 years ago and that manufacturing initiatives. So there is a little bit more interest in manufacturing, which went by the wayside in the 80s to 2000. Whether it is sustains, we don't know.
Yeah. So before we finish up, I'd like to put Vivek on the spot, our next gen. Vivek, do you have any thoughts as the budding researcher, academic researcher, on what you heard today?
Yeah, I mean, first of all, this was a really interesting talk. Part of the reason why my dad invited me is I actually do a lot of work with AM in the heat transfer space. Yeah, I think there is that gap between what we talk about in universities and especially the undergraduate level, and then how that translates into the into the real world. I think the consumer grade 3D printing, kind of the toys that were on the second or or third slide has plenty of kind of penetration into the academic area. I mean, most students at some point in their academic careers will use some sort of 3D printer, and you know, actually to kind of speak to a different question too, that's where China has a lot of innovation. So most of the consumer grade 3D printers that you've heard of, Creality, Bamboo Lab, all of those companies are all Chinese companies. But you know, like Uncle was saying, as soon as you talk about anything more advanced, you know, most of the manufacturing knowledge, even in places like Georgia Tech and Illinois, which are kind of big legacy manufacturing schools, you know, you learn how to do a mill, you know how to do a lathe, and then that's kind of it. So I think the need that Uncle described is absolutely still there. I think the manufacturing courses that exist still only cover the legacy stuff, and you need to go take advanced classes if you want anything else. But you know, the work we do is really interesting. We do a lot of both the macro scale topology optimization for, you know, increasing heat transfer coefficients and heat exchangers and stuff like that. And I also appreciated the point about the difference between 3D printing and additive manufacturing, because we work with a company called Fabricate Labs, which does a lot of different additive manufacturing techniques that isn't just 3D printing. So even just that misconception that exists in a lot of places of, you know, every additive manufacturing process is a 3D printer, I think even just correcting that somewhere down the line is an interesting idea. But I also agreed with the anecdote of, you know, you buy this thousands of dollar 3D printer and then, you know, one person uses it. That's kind of how it is in our lab, that we have a bunch of at least consumer grade 3D printers, and then, you know, no one uses them but me. So yeah, there are a lot of cool things, and I think one of the things that may be interesting is how we translate the consumer and the industrial processes together. You know, one interesting thing that's coming up is that now there are printers that can print metal filament, and then you just burn their metal particles in standard plastic, and then you burn off and sinter. You debind the PLA in a sintering oven, and then you sinter it again to get the full object. And I think that's maybe helping people get a better understanding of the potential of AM beyond just, you know, a fidget toy or whatever. So I don't know if that was a useful perspective, but that's what I've been seeing.
Yeah, definitely, Vivek. Thanks for your thoughts.
Yeah, Vivek, you hit everything on the nail, beautifully summarized. And I'll add, just medical industry seem to pick up a little bit more interest. And I am betting on them outside of the defense industries and large manufacturers to see some breakthrough results, because they seem to be a little bit more interested, because the customization is of great interest to them. So let's see if that, and also some other bone structure thing, they seem to think lightweight, and these things mimic what we see in our bones. So we'll see if that plays a role.
So Sundar, one quick question. Do you see a lot of applications where they're using this method to create wax patterns for ultimately using them into like a, making a lost wax process? You know what I'm saying? That you could use sinter, you can make wax patterns and then use that to make the metal part.
Yeah, well, I don't know exactly about the wax thing. I can look into it, but I know lots and lots of people use this to make their tools, or use this as a tool. You know, they don't actually make the part with it. They just make the tool with it and then use the tool to make the part. So if you put that in the category, the wax will come in the same thing, because they don't worry about the mechanical properties or anything else, except they want the tool so they can use the tool. I don't know. It's by way. I think what you said makes sense. I bet there is somebody who's doing it.
Well, we make use of the what you call as the 3D printing toy makers to make tools.
Yeah.
Honestly, we in
Yeah,
our
but I know. Yeah.
use,
So that I didn't mention that, but that's a great application domain. Yeah.
okay, thanks.
What
Yeah,
3D printer
thanks.
do you have, Dilip? Sorry, time. We are out of time. We'll talk later.
Now, thanks, Dilip, and also Sanjay for your perspectives, and maybe Navjit as well from, I mean, from the industry point of view. And yeah, we have been at this for about 90 minutes, so maybe we can bring it to a close. But I mean, I see someone signed as Motorola Moto. Can you identify yourself so that we know who you are, and maybe others know who you are? You're muted. Well, if not,
I think
well,
that's Jha.
Yeah,
pardon me?
Bala's there. Yeah. Go ahead, Kayla.
Yeah, Bala is there. Oh, okay. Yeah, that is. Who did you say it is, Bala? Krishna?
I thought it was Jha.
Ja, okay, thank you. Okay. Well, if there are no further questions, of course, you can all reach Sundar offline. And thank you, Sundar. Very stimulating talk. And yeah, all of you have a great long weekend here in the US, President's Day holiday Monday. So,
And the slides will be posted in
I can post
3
the
days.
slides ASAP. I will let somebody else do the video part. I'll post the slides. I don't know how to do that. I can send Arul the slides and he can choose how he want to play it. Either want to
yeah, why
post
don't you
it or-
just post it on our SDG
there.
group for starters, and then
Okay,
I'm sure
great.
Kushru and or SAP will post it elsewhere.
Sounds good. Okay, will do.
Okay.
Thank
so-
you.
Yeah, thank you
Thanks
all.
again. Thanks again for a great talk, sir.
Bye.
Bye-bye.
Thank you, guys. Have a great afternoon here and have a great evening over there.
Okay, bye.